Gazing down from space, we marvel at Earth's bountiful oceans and continents, its life-giving atmosphere. We ask, how did our planet begin? How did it come to support life? And life to support Earth? To find out, we peer back in time, some 5 billion years ago. The story of Earth starts within a giant spiral galaxy, the Milky Way. At 100,000 light-years across, the galaxy is a cauldron of swirling dust clouds and glowing gas. This simulated view shows a 50 million year span, a cosmological blink of an eye. In that time, millions of giant stars live and die in staggering explosions called supernovae, shown here as flashes of light. They seed the cosmos with the stuff of planets: carbon, silicon, iron, and more. In one distant corner of the galaxy, a supernova shockwave slams into a cloud already rich with these elements. The impact collapses the cloud, sending stardust streaming into its core. The cloud is about as cold as the universe gets, but the tighter it's packed, the more it heats up. A storm erupts at its center, a vast raging hurricane of dust, gas, and ice crystals. In its eye, temperatures soar. A star ignites. Our sun is born. It is being fed by a slowly spinning disk, the cradle of our solar system. Within the disk, planets take shape in a long and violent process. It starts with dust, gathering into sand-like grains. They form pebble-sized objects within clouds of loose gravel. Over millions of years, gravity draws them together to form rocks, ice balls, and boulders. These objects coalesce into miniature planets, or planetesimals. One such body, the primordial Earth, is growing steadily, but its fate hangs in the balance. What began as a gentle mingling of matter is about to get ugly. A computer model recreates the first 100 million years of our solar system by simulating the interaction of dust, gas, ice, and boulders. Each flash marks a collision. Each ring tracks the orbit of a would-be planet. While some break apart in collisions, others grow large. Out on the periphery, far from the sun, a giant emerges. Jupiter. Within 1 million years of its birth, Jupiter succumbs to the gravitational pull of the inner solar system. It begins to spiral toward the sun. Scientists call Jupiter's big move the Grand Tack, named for the turn a sailboat takes into the wind. Along the way, Jupiter plows through clouds of cosmic debris. What it does not swallow, it flings out of the solar system. The closer Jupiter draws toward the sun, the more cosmic clutter it clears away. Jupiter moves all the way into the orbit of present-day Mars. Ultimately, another giant planet, Saturn, grows large enough to pull it back out. Jupiter's Grand Tack has reduced the mass of the inner solar system. Now, any planets that form there will be relatively small. That includes Earth. Earth is still just an embryo of the planet it would one day become. Now that Jupiter has moved back out, Earth and up to 30 hungry competitors are free to scour the inner solar system for scraps. They blend together. They blow apart. Which ones will survive depends on the luck of the cosmic draw. In one heady 50 million year run, the roller derby of planets goes wild. As the remaining planets tug on one another, their orbits destabilize. A new round of collisions leaves just a handful of would-be worlds. The time is about 4.5 billion years ago. Earth may harbor volcanoes on its surface and a thin, toxic atmosphere. Our planet has so far withstood the onslaught of planet formation. It now awaits the test of its life. Another planet, about half its size, is closing in. This is Theia, a world that might have been. Instead, its journey ends here as it bears down on Earth. Imagine the view from Earth as the ultimate threat looms large on the horizon. Theia rocks Earth to the core. According to one major theory, Theia shears away a third of the planet. But instead of destroying our world, Theia becomes part of it. A computer simulation captures the first 24 hours. Debris unleashed by the collision envelops the Earth in a dense atmosphere of vaporized rock. The cloud coalesces into a ring, a belt of molten rubble. Much of the orbiting debris rains back to the surface. But within a century, what's left gathers into a single, wondrous body. Earth's companion, the Moon. After the impact, our planet is left spinning rapidly on a slightly tilted axis. The Moon orbits much closer to Earth than it does today. From its surface, our world would have filled the sky. As the Moon gradually slips into a more distant orbit, it exerts a drag on Earth. It slows our planet's spin and steadies its tilt. The Moon serves as a reminder of the cataclysm that almost spelled the end of our planet. But from here on, it would be a welcome constant, a source of stability and ultimately, beauty. For the next tens of millions of years, the steady barrage of debris from space does not let up. But asteroids don't just rain hardship. They also carry massive amounts of water. The pummeling may also have released water, bound to minerals deep beneath the surface. Half a billion years after the birth of the Moon, Earth has cooled dramatically. It's now a world of water. Its seas span every horizon, broken only by volcanic islands. It's also rich with chemicals, with all the carbon, nitrogen, oxygen, iron, and more that came with the dawn of the solar system. The planet has everything it needs to accomplish its ultimate feat, producing life. But there's a problem. Its water is disappearing. The young sun is prone to powerful flares that strike the upper atmosphere. When a solar particle hits a water molecule, H2O, it can blast it apart. lightweight hydrogen wafts into space, while heavier oxygen sinks to the surface and binds with rocks. Through this process, solar radiation would ultimately strip our neighbors Mars and Venus of water. To avoid that fate, Earth is in a race to give life a foothold before its water runs out. Incredibly, life itself may hold the answer. A process that keeps living organisms alive might also keep the world wet. On the fringe of volcanic springs, they're cooking away. Proteins and nucleic acids, the chemistry of life. We don't know exactly how life sprang from cauldrons like these. What we know is that life did emerge, and that it spread, thanks to a key breakthrough, the ability to turn sunlight into energy. Photosynthesis, the process that fuels plant life, made its first appearance in simple bacteria over 3 billion years ago. Using one of the world's most powerful supercomputers, scientists have sought to model its chemical secrets. Step 1 is to capture sunlight. Passing through a transparent membrane to the center of the bacteria, we encounter a cluster of spherical pods. Each one is equipped with special sensors designed to harvest solar energy. When a photon hits, it excites rings of chlorophyll molecules. This energy is transferred across a family of proteins, the machines of life. Down the line, electrons and protons carry the energy through a chain of chemical reactions. The energy driving these reactions came from the sun. The cell must now convert it into action. It's the energy stored in protons that gets things moving. Streaming into watery spaces within the cell, they flow toward a towering molecular structure. As they enter, their electrical charges turn a protein like a crank. This turning motion initiates a chemical reaction, one that is essential to all life on Earth. Two molecules join to form a third, called ATP, shown in blue. It is the universal energy currency in every cell that has ever lived. Like a biological battery, ATP stores energy captured from the sun, repackaged in a stable form that the cell can now use. To break down food, to power locomotion, to fuel reproduction, to live. ATP made it possible for microorganisms to flourish and evolve. As bacteria gave rise to plants, a more advanced form of photosynthesis released a byproduct, oxygen. Over time, this new supply of oxygen would change the chemical composition of the atmosphere and stem the loss of water. Earth avoided the fate that befell its neighbors as life spread to its every nook and cranny. Earth today, endowed with ocean, atmosphere, and land, with light and warmth, with life that's bountiful and in balance. But think of all it took to achieve that. The aftershocks of a supernova, the violence of Jupiter, a chance collision, and the gift of a moon, of water and life. The more we're able to reconstruct our past, the more singular it seems. That is, until we realize how very many other solar systems are out there. We ask, is Earth just one of countless life-bearing worlds in a galaxy bursting with life? Or is it a wondrous twist of fate, a remarkable convergence of chemistry, energy, and chance? Our planet became a paradise. But is it the only one?
Okay, that is your show. If you have any questions for me, you can come back up here. I'll do my best to answer them. But if not, enjoy the rest of your Sunday here at the Planetario. Thanks for coming.